In this chapter, we will deal with shearing stresses in beams and thin walled members. To start with, until now, we have considered for transverse loading, we limited our analysis to the normal stresses caused by bending moments, since they are the dominant criterion in the design process. But also, transverse load will create shearing stresses. This is why when we design beams with particular cross sections, shearing stresses can become important, and therefore their analysis should be considered in addition to the analysis of bending moments. In the following picture, you can see a reinforced duct which is attached to each of the steel sections shown to form a composite box bridge. So our purpose then is to see that in some cases, shearing stresses can be of high importance and should be treated to make sure that we are not overcoming the shearing stress limit of the material used. We already have developed together, in case of transverse loading applied to a beam, that will result in a normal and shearing stresses in transverse sections. And we have seen that the distribution of normal and shearing stresses should satisfy the following equations. So whenever you have transverse load, this will lead to the creation of bending moments in your beam, in addition to the shear forces in the plane of the section. And we have discussed together how to get V and M over the beam through different methods. We use the area method, we use the section method to find the graphs of V and M. In the previous chapter, after drawing V and M, we considered the design based on not exceeding the limit of compression and tension, and we found what should be the maximum bending moment used. In this chapter, we will continue in this analysis. We'll consider transverse loading, but will not limit ourselves to the design of bending moments, but also to the determination of the maximum shear that is allowed. And based on this, we can have an overall idea about the limits we should put on our transverse load and if it will lead to possible fracture or not of our beam. So here you can see the results of transverse loading. So as we mentioned already, transverse loading will lead to two aspects: the creation of bending moments and the creation of shear forces. This is why when you consider a certain cross section, within the cross section, you have the normal stress distribution will create the bending moment, while the shear stress distribution will be created by tau that is applied to each element, will result in a total shear force. And when you draw the shear and bending moment diagram, you determine the total shear force in each cross section, but this shear force is created by a certain distribution of shear stresses within the area, as was the case with the normal stress distribution that will create a total bending moment. In this chapter, our purpose is to determine how will be the distribution of shear stresses. We have seen that for normal stresses, a linear distribution will be created, and at the neutral axis, sigma is 0, in a way to have a total moment equal to the bending moment. Now here, same analysis will find what is the distribution of shear stresses over the cross-sectional area that will lead to a total shear force of V within the cross-section. Now, if you consider the following figure, we can see that for any element, okay, whenever we have shearing stresses in a certain plane, this will create automatically equal stresses in the horizontal faces. Why? Because if you look at this figure here, whenever you have shear forces, if you take a certain small element of your beam, you have shear forces developed in this cross section. So this will result in a certain distribution of shear stresses. If you take the face that is just opposite, you will have an opposite shear stress, and this will create, if you want, like a couple. So to have your element in equilibrium, you should have on horizontal faces also development of shear stresses in a way to create an opposite couple to keep your element into equilibrium. This is why we say that whenever we have shear stresses tau xy, this will result to the formation of shear stresses tau yx. And to remind you, whenever we have shear stresses, we consider two subscripts. X is the first subscript represents the vector normal to the face we are considering, and the second subscript represents the direction along which we have the shear stress. So here this is tau xy. So tau xy will lead to the presence also of tau yx. Now, so as we discussed, if tau xy is present, then tau yx also must be present. This means that longitudinal shearing stresses must exist in any member subjected to transverse loading. And to see this effect, we can consider the following cantilever beam made of separate planks that are clamped together at one end here. When subjected to a transverse load, so if you put a force P in the transverse direction on this beam, you will observe like tendency to slide between these different planks. And this is due to the presence of or development of shear stresses in this direction. Okay, so while sliding does not exist, the tendency to slide does exist, showing that stresses occur on longitudinal and transverse planes. What do we mean by this? So now, in the first figure, you have ability of sliding between the different parts, okay, because they are not adhering to each other. However, in the following figure here, when you adhere all planks together, then the tendency to slide will be opposed. And this opposition will be by development of shear stresses to oppose the sliding effects between the different planks. Okay, so when a moment M is applied, the planks will bend into concentric arcs of circle and will not slide, therefore verifying the fact that shear does not occur in a beam subjected to pure bending. So if we compare the two cases of transverse load and bending moment applied, okay, whenever you have a certain beam where your different parts are rigid or adhering to each other, and you apply a transverse load, because they are adhering to each other, the tendency to slide will be opposed by shearing effects. However, if you apply a bending moment, then you will not observe any sliding effect. And even if you consider this case where you have possibility of sliding, whenever you put a bending moment will not lead to any sliding between the parts. You will only observe curvature without any sliding effect, because the bending moment will lead only to normal stress distribution. However, the transverse load will create ability to slide, to have sliding between the different parts. And when they are adhering to each other, the shear stresses will be developed to oppose the possibility of sliding. However, in bending moment, when you apply just a bending moment on your a certain couple on your structure, so you will have only in any cross section a bending moment to oppose it, and then the bending moment will not lead to any shear stresses, because it will just lead to development of normal stresses. And we can verify this easily from this figure, when we apply a transverse load on separated planks, we can see that they will tend to slip with respect to each other. However, when we apply bending moment on them, they will just tend to have a certain curvature, and they will bend. Now, we move to the analytical analysis, how we can do the analysis of effect of transverse load on shear stress distribution. Let us consider the following beam. The following beam is subjected to variable loads, concentrated and distributed loads. And now we want to do the analysis on a certain part of the beam. So if I consider a part of the beam and I take a very small element, so I will do analysis of element CD, D prime, C prime, which is of length delta X. And I want to see what is happening over this element. Okay, so first, this element here, as you can see at sea level, you have a distributed load. So if I illustrate this element is subjected to a distributed load omega downward, and we consider that W is positive downward. So if I consider now the analysis, the equilibrium analysis of this element, because you know that any structure in statics, when you do the free body diagram of it, sum of forces on it will be equal to 0. And because we did a cut here and here, so the internal forces at this level will become external forces. So when you do a cut on this face, you will observe now the normal stress distribution along this face. And when you do a cut at D level, you will observe the normal stress distribution on this face. And for this one, for this face, longitudinal face, we will try to find the shear stresses developed. Okay? So if we do the equilibrium analysis of this portion, we can say that sum of forces on it is equal to 0. So the force parallel to X direction is called delta H. So plus delta H, and if I consider the distribution of stresses here, so this distribution of stresses along X direction is integral over the area. So I have here equal areas here, and I will integrate the normal stress distribution. So I will integrate at this face sigma D and at this face sigma C. Because sigma is here is represented as compression stresses, so already the value of sigma is already negative. Okay, this is why I just did plus integral sigma D minus sigma C dA. Sigma D will be negative and sigma C will be positive. Okay, so this will lead to the following interpretation, that I have in total, to have sum of forces along X equal to 0, I have delta H plus integral over A sigma D minus sigma C dA equals to 0. And now I know that I can replace sigma by minus M over I times what? This is from previous chapter. Okay, so the expression of the normal stress at any location y from the neutral axis is minus my over I. So now when I integrate, and this, since m is constant, so for a certain cross section I know the bending moment, and I represent the inertia of the cross section about the neutral axis, as you can see here. So I can take minus m over I outside the integral, and then what do I get? So by replacing sigma d first by minus md y over I, and I have minus sigma c will become plus m at c over I y times dA. Now taking y into factor, because it's common between the two terms, I get the following. I get that this is equal to mc minus md over I times y dA. And of course, as we discussed, mc minus md over I is constant. So it's not varying over the cross-sectional area. I can take it outside of the integral, and then I am left with mc. So when I integrate this term, it's equal to mc minus md over I integral y dA. And this term plus delta h is equal to 0. So now, taking this term to the other side of the equation, I get that delta h is equal to md minus mc over I integral over a y dA. And the area I am integrating over is this one, the area over which I did the cut. Okay, so what can I deduce now? I can deduce that the forces developed in x direction will be related to the variation of bending moment in between C and D, and is related to whenever I do integral y dA can be replaced by y star times the total area of the cross section. So we'll discuss this in the coming slides. So if I go back to my analysis here, I can say that I have that md minus mc, which is affecting delta h, is equal to delta m equals to v delta x, because we know that already shear is related to moments through this equation. And this is the basic equation used in area method, that the variation of m is equal to the area under shear curve. And because we consider delta x very small, we can say that delta m is v times delta x. Now, what about integral y dA? Integral y dA represents what we call the first moment with respect to the neutral axis of the cross section, and it can be replaced by y star of the section we are considering times the area y star, which is the centroid of the area we consider, times dA. So if you go back to this figure, you are integrating over this area. Let us see here. We show the element. So this is my cross section, let's say. Okay, this is my cross section. The area of interest is limited here at this level from C to C prime. So if I look at my figure, when I do integral y dA, it's relative to this area. And I can replace integral y dA by y star times A, where y star represents the centroid position of this area, of course, relative to the neutral axis, times the area of concern. This is my area from the top to the level where I did the cut here. Okay, so now if I replace back integral y dA by y star A, or what we call Q, which is the first moment with respect to the neutral axis of the corresponding cross section, and I replace the difference between md minus mc, which is delta m, by v delta x, I get a relation between the horizontal force developed and the shear stress and the shear force, sorry, in the cross section. So I can say that delta H is VQ over I times delta X. And this is how we can relate the total shear force developed to the force that is parallel to x-axis created due to, if you want, shear along the parallel direction to the x-axis. And this will help us now in future, in next slides, to see how we relate shear stresses to V. Okay, so until now we have developed an expression for the force over a certain distance delta x. In general, we are interested in forces per unit length. So if I divide the length is delta x, if I divide here this expression of delta h by delta x here will be simplified, and then I can find that if I define a certain parameter q and I call it the shear flow, which is delta h over delta x, I can find the horizontal shear per unit length, and this horizontal shear per unit length will be equal to VQ over I. Now, whenever I want to calculate the shear flow, I can demonstrate that the shear flow on the upper area is equal in magnitude but opposite in direction to the shear flow on the lower area. Why? Because if you consider the following cut, if you do a cut at this level, okay, of course by action reaction, the force done, when you do a cut on this part, let's say you have delta H in this direction. If you take the lower part and you represent it, for the lower part by action reaction, the force developed will be in the opposite direction. So you will have delta H, but like this. So this is delta H prime. Delta H prime is equal in magnitude to delta H and will have same direction but opposite sides. Okay. So what we have then is that Q prime developed on the shear flow of the low area is delta H prime over delta X, is VQ prime over I is minus Q. And we can say also that if we consider the whole area, it's evident, we can demonstrate in another way that Q and Q prime are opposite. Because if you consider the whole area, if you consider the whole area, integral YdA of the whole area will be equal to 0. Why it's equal to 0? Because we know that integral YdA of an area is Y centroid times total area. But we know that here we are dealing with Y from the neutral axis. So the origin of Y is on the neutral axis. So when you take the whole area, integral YdA will give you Y of the centroid. And since the centroid is on the neutral axis, then integral YdA for the whole area is 0. And this, if you want, term can be decomposed into two parts. You can say that integral YdA is equal to the integration over the upper area plus the integration over the lower area. So you can say that integral YdA is equal to Q, which is the first moment of the upper area above the neutral axis, plus Q prime, which is the first moment about the neutral axis for the lower part. And since when you do the summation of these two, you cover the whole area, then this is equal to integral YdA over the whole area equals to 0. So Q is equal to minus Q prime. And of course, this is expected because by action reaction, delta H prime is equal to minus delta H. So whenever you do an analysis, you can say that if I consider the upper area, I can deduce the shear flow on the lower area. Now, what about the expression of the shearing stress? We said that we will start from delta H in order to get an idea about the shear stress distribution. So here, we can go back to the definition of shear stress. So what is the shear stress? The shear stress is the shear force per unit area. We have already calculated delta H. So delta H is the shear flow Q times delta X. And we have found together an expression for the shear flow Q. We have seen that the shear flow Q can be written as VQ over I. And delta A, which is the area on which the delta H force is acting, is equal to delta X times the thickness of the beam where we did the cut. Okay, so now delta X will be simplified, and then the expression of tau, the average shear stress in the cross section considered. So as you can see in this figure here, okay, you have you did a cut, in your beam. This cut is characterized by a certain width delta X and by a certain thickness T. So this is T and this is delta X. So you can say that the force delta H is acting on the following area. So let us see it here. So here, if you take the bottom part, you have delta H prime opposite to delta H acting on this area. And this area has a width of delta X and the thickness of T. So delta A is T times delta X. And this is the area over which the force is acting. So the shearing stress, the average value of shear stress, can be calculated as delta H over delta A, replacing delta H by its value, which is Q delta X, and delta A by T delta X. I can find that tau, the average stress developed in this section, is VQ over IT. Okay. Now, of course, if you consider the upper surface and the lower surface of the beam, the shear developed at these levels will be zero, because at these levels you have that the value of Q is zero. So you don't have already, when you do a cut, you don't have any area above this level. So you don't have a first moment about the neutral axis, and then Q will be zero. This is why for upper face and bottom face, okay, we have that the shear developed is zero. So you have only a shear development within your, and this is logical. And for shear stresses, it's between two parts. You don't have here, it's exposed to it's a free surface. So on free surfaces, you don't have development of shear stress. And you can find this from the equation, since at bottom and top surfaces, the value of Q is zero. Now, in reality, why we are here talking about an average tau? Because in reality, you have a variation of the shear stress. And you have, for example, here, whenever at the corners, at the extremities, you have like larger value of shear stresses compared to the center. So as you can see here, you have high value of stresses at extremities and smaller values here. But in general, if the width of the beam remains small compared to its depth, then you can neglect, if you want, the shearing stress variation. You will have slight variation over line D1 prime, D2 prime. Now, let us consider shearing stresses in common beams. So first, if we consider a rectangular cross section. So in rectangular cross section, if you want to apply the rule to find the shear stress distribution, Let us first consider at any level. So if I do a cut at this level here, okay, and I want to find the expression of Q, then this will be my area of interest, the area above the cut, or I can take also the area below the cut. But here this part is easier, okay? Now, so I did the cut at level Y. This means that if I know that the total height of my rectangle is H, so if this is H, and I did the cut at Y, then this distance here is equal to H minus Y. And since I want to calculate the first moment of this area relative to the neutral axis, I should find the position of the centroid of this area. The centroid of this area is at half of this distance. So I can say that this length from this point to this one is H minus Y over 2. So this distance is H minus Y over 2. And therefore, Y of C prime, so if I want to find from the neutral axis what is Y bar, then simply Y bar is equal to this length from this level to the top, which is H over 2. So this is H over 2 minus this distance, which is between the top level and the center level here. So it's equal to minus H minus